Try to be familiar with going back and forth. So you've got a Caribou card, and you buy your daily $3 cup of coffee, and after today's purchase, you were told that you had $35 left. Let's write a recursive formula to model our daily balance after today. That means that right now, I'm starting with a balance of 35. And from now on, my UN will be UN minus 1. And what happens each day? You minus 3, because your coffee costs $3. So that's the recursive formula, something we've been working with for a whole chapter. And now what we're going to do is we're going to translate that into our explicit formula. So now we have y equals, and since the slope is whatever we're going down or up by each time, I have negative 3x, because negative 3 is my slope. And I started at 35, which is my y-intercept. So it's plus 35. And you can kind of see where those numbers come from in both cases. So you can go back and forth now between the two. What I would like you to try to do is part C. I want you to try and sketch it. Make sure you put some kind of scale on your axes. And then tell me whether it's continuous or discrete. I'll give you 2 minutes. Okay, so as I was looking at this one, we know that we start at 35. I know I'm going down by 3 each time. So this is kind of an example. Don't forget that on your vertical axis, you should probably label that this is money. And then as you're going down here, this is your days, each day, how many days have gone by. I don't really know why I picked 3 days at a time. Maybe in my head it's stuck that we were going down by $3. You could go up by 1 day. It's not really going to matter, I don't think. And as I look at this situation, and I look at this, notice that when I go down by a day each time, there are dots each time. So the big question is, do I connect these dots or do I not connect them? Meaning, do I buy a coffee every single moment, or is it only once in a while that I'm doing this? Once in a while. So that means that we're talking about something that's discrete. We don't want to connect these dots. These are individual points that gives us information, kind of like a scatter plot. It looks like it's linear because we're going down by the same rate each time. That's $3 each time we do this. Questions on that? You should see a graph that looks like this. Your graph might not be exactly like mine. Your scale on the left or on the vertical axis and the scale on the horizontal might be different, but you should see a line. Yes, sir. So let's look at recursive equation number 1. So here's recursive equation number 1. Bless you. It says my starting value is 4, and I'm going down 1 unit each time. Is there a matching graph? B is correct. So the B graph matches with that recursive equation. Is there an explicit equation that matches? No. So what we're going to have to do is we're going to have to create our own. So the one that we would create to go with this stuff. So we had recursive equation number 1. Oh, I didn't want that color, sorry. Recursive equation number 1 goes with graph letter B, but there was no explicit equation. So I write down y equals
4 plus negative x.
4 plus negative x or 4 minus 1x. Both are good, or negative 1x plus 4, negative x plus 4, any of those are acceptable. Remember, the number with the x is always the slope, whether I put the x first or last, and the number not with the x is the intercept. So that's recursive equation number 1. Number 2. That's great. Number 2. Start at 2 and go up by 5. Start at 2 and go up by 5. Do any of those match? C looks like it matches, so here's graph. Oh my goodness, what is my deal today? Sorry. Graph C looks like it matches. I have the crossing of the y-axis at 2, and I went up 1, 2, 3, 4, 5 for the one that I moved over. And is there an explicit equation that matches that? It does look like number 3 works out well. So those 3 work together, and so I know that recursive equation number 2 goes with letter C, and this one is III, or number 3, Roman numeral, I guess. So that, at least that one had a complete match. The last one is recursive equation number 3. Does it have a matching graph? Well, it has to intersect the y-axis at -4. Letter A is intersecting at +3. So, nope. And it's going up by 2, not 3. Correct. Good job. So, the problem for us is that if we're talking about recursive equation number 3, there is no graph that matches it. If I wanted to write an equation, I would be writing y equals, my slope is 3, so I'd write down 3x. My y-intercept is -4. Notice that in the red and in the brown equations, in one of them I put the y-intercept first and the slope with the x second, and then in the brown I did the reverse. It doesn't matter which way you write it, I don't care. They both are explicit equations. Okay, so you feel free to write it either way.
Wait, that's a number for the explicit formula.
So it was just noticed that if we're looking at recursive equation number 3, that matches letter I. So this is the same as the explicit formula that we wrote down that was in the reverse order. Good catch. And then the last thing is, are the points n and un, which is really talking about your x value and your y value, of an arithmetic sequence always collinear? And the answer is yes, because the rate of change is constant. And what that's saying is that in each of these cases, red, blue, and brown, I'm going up or down by the same amount each time. So in the red, for example, I was going down 1 unit each time. In the brown, I was going up 3 units each time. And since that's true, that's why they're collinear. If you were multiplying by a decimal, like 0.75, like we've done in the past, that's not collinear.